Welcome back. I'm Alex Wood, and with me is Ed Mackey from Analytical Graphics, and we're going to continue our video series. Last video, we went through how to create a UV map, and now we're going to actually put some texture data in that UV map. So, Ed?
All right. So let's start by learning a little bit about this texture noise that I plan to put on this model. Here we have our CubeSat model. It's got just placeholder textures on it.
What's the metal look like right now? What do we? It does have a metallic value.
It does have a metallic value, but it's fairly rough.
It's just a uniform.
It's a uniform metal, and this thing that we'd been calling the pocket up here is that same material. I would like to give it more of a brushed aluminum type of feel. So let's take a quick look at some fractal noise, because that's always fun to look at. I'm going to turn my CubeSat off. Let's leave that on for scale for just a second. And I'm going to add a test cube. That's way too big. And my test cube is going to show us what this noise texture is going to look like. So we'll jump over to the shading panel. Here's a leftover texture map from before that I will clear out. And we will zoom in on my test cube. This is a noise test. And it needs a material. I will give it a noise test material. And for this material, I don't want to actually see all these lighting effects that are on this cube. I just want to see the effect of the procedural texture map that I'm attempting to assign. So I'm going to set the base color to black. And my cube is still pretty shiny, so I'm going to crank metallic up to 1. And now I have almost no light at all coming off of this cube. There's a 3D cursor is still sort of in the way. I'm going to pull that out of there. So now we're really seeing nothing at all in this cube, and now I can add something brand new into it, and we'll take a quick look. I'm going to add the Musgrave texture. This is F. Kenton Musgrave. Figured out how to combine multiple octaves of procedural noise to create this texture. I'm going to connect it to the emission channel. And the reason I connect it to the emission channel is, and my cube looks like a cow now. I love it.
I think we're done.
I think we're done here. Done. Wrap it up. The reason I connected it to the emission channel is we don't have any sort of lighting effects from any light sources. We're just seeing the raw output of this noise texture map here. And there's a couple of parameters on here. There's a scale. And if you look at scale, you can see that it's scaling from one corner of the cube. And for my demo, I would like to control where that origin is. So I'm going to put a geometry node in here. I would like it to use world position space and not just bounding box space as the source of the noise. Now, when I do that, something a little more interesting is going to happen. This noise appears to become very swirly, like that. And it has another interesting property that I will attempt to show here as well. I'm going to select just the topmost face of this cube, and I'm going to move it up and down with GZ. And you can see it sort of swirling hypnotically here. But if you watch what's happening at the boundary edge between the top face and any of the side faces, it will actually look like the top is painting the sides as it goes. So wherever the bulges appear in the top, it leaves behind traces on the sides.
It's like we're slicing through a volume here.
We are indeed slicing through. It's as if the entire universe is filled with this three-dimensional volume of noise. And the various faces of this cube are simply providing two-dimensional glimpses into that three-dimensional world of noise. So that's kind of an interesting way to think about this. It's a good way to think about it because it's what it's doing. I am going to put this one top face right at 0, cutting my cube in half. And the reason I've done that is because I'm going to show what is happening at that world origin. So if I do my scale now, you'll actually see it's scaling from that middle point. On the other faces, you will not see that. On the other faces, you will still see a swirl like that. But on this face, because I'm cutting through a three-dimensional origin of 0, 0, 0, the scaling happens there. The other thing I would like to point out is that these lumps are all very similar in size. And actually, before I point that out too strongly, I'm going to just dump some numbers in here. What I'm trying to get us into is a state like this, where we're seeing actually just what I'm going to call a single octave of noise. So procedural noise, in this case, the fractal bump map, the fBM, consists of multiple octaves. And each octave is a collection of lumps of random shape, but of all mostly uniform size. So if we zoom out, for example, we don't see any really big lumps. And if we zoom in, we don't really see any small details. It's all random, but it's all fairly uniform scale. So that's the scale. We also have this control called detail. Detail is actually the number of octaves. If I crank it up now with the settings I have, you'll see it's just getting brighter. It's not doing a lot besides getting brighter and dimmer. I'm going to ask for 8 octaves of noise here. What may not be totally apparent is that all of my octaves of noise are all identical right now. They're all overlapping, and so when I ask for 8 of them, they're all just stacking up identically, one on top of the next. And that's happening on all of my faces here. So there's a parameter in here that controls how these octaves differ from one another. And it's my favorite term in all of procedural texturing. It's the Lacanarity. No one seems to know what that term means. So it's great to say Lacanarity with great authority because it intimidates everyone you're talking to.
Yep. We're actually going to be one of the, we're going to have the YouTube video that has the most occurrences of Lacanarity.
Lacanarity. I wonder if there's a record for that.
We are going to hold that record.
So what happens if I mess with that one? The whole thing explodes or implodes, depending on your point of view. What Lacanarity actually is, it is a scaling factor between octaves of noise. So I've asked for 8 octaves, and each octave has its noise coordinates multiplied by a scaling factor of 1.2. And that means each successive higher octave is actually showing us visually smaller and smaller details.
And we actually get a good glimpse into that Lacanarity by looking at the top of this where it's centered at 0, 0. But on the sides, we're looking at how that is projected on the outer regions of that.
Yes, on the sides, we
geometry.
don't see evidence of that central point. And the reason is that these are 3-dimensional coordinates, and they are being projected, right? So these, each one of these dots that we see on the side here is probably indicative of an entire column of noise shooting out from the central point. But because it's happening perpendicular to the plane, a user looking at this plane will never know that that's really happening. It's only when you're looking at something that's coplanar with the 3-dimensional origin that you see that this has happened. So if you feel the gray matter like expanding inside your head, that's a good effect to have from looking at this. 1.2 is a terrible value to use for Lacanarity because of this effect that looks like picture-in-picture. But I'm going to stick with it for one more moment here. There's one parameter that I did not yet talk about, which is dimension. And if I crank up the dimension, you'll notice we've lost our picture-in-picture effect, and we've gone back to what appears to be just that first octave of noise. So dimension then is the it reduces the influence of successive octaves. So when it's down at 0, and I've asked for 8 octaves with 0 quote unquote dimension, it's giving me all 8 octaves at full strength. And if I crank it up just a little bit, what you'll start to see in here is that some of these smaller octaves, the higher ones that have more fine details, are getting toned down by that. And that's going to become important here in just a moment. So let's go back to a more correct value for Lacanarity, which would be 2.0. 2.0 is the default, and it's probably a good value to stick with. It means that each octave of noise has twice the scale of the previous octave. And the idea behind that is you shouldn't be able to see a repeating pattern as we were seeing from one octave to the next. Each octave should be essentially, by virtue of having its coordinates doubled, it should be in a totally different location. It should be a different patch of noise. And it has twice the scale or twice the density of the previous octave. And now we're starting to see something that maybe looks a little bit more like actual clouds or natural looking cloud patterns. And what you're really seeing there, of course, is this first octave is providing these big lumps of white and black. And then the successive octaves are providing all these little details. So if I take dimension down to 0, you see this gritty, grainy texture. All of these little details are at full strength and are punching holes in the big white area that was left by the first octave. But if we tone down those smaller octaves, I like to use about 0.7, then they don't punch holes in the original first octave of noise. They just provide a little bit of modulation and detail on it. You get a nice cloud pattern. So that's a fractal bump map. There's another thing that may be worth knowing about that is that we've only been seeing the positive side. We've been only seeing the 0 to positive 1 range here. The noise actually equally goes above and below 0. So I'm going to add a new map range node in here, stick it right in here. And on this map range, rather than taking the input from 0 to 1, I'm actually going to take the input from -1 to 1. And you'll see a lot more detail coming into view because the noise, it's like a waveform. It's numbers going up and down, above and below 0. That's great, but it doesn't look anything like brushed metal. What do we do about that? Well, the simplest thing to do about that is just to stretch it. So to stretch the noise, we're going to mess with the input coordinates, those 3D coordinates that are controlling where we are in our volume of noise. I'll do that with a vector math node, like so. I'm going to multiply my coordinates, not by 0 because they will have zeroed out. So now, right now, I'm multiplying them by 1, so nothing has really changed. But I'll take the x-axis and stretch it a bit. I think stretch it pretty well there, and we can even take another axis and crush it. So now we have noise that has been stretched, especially along this axis, but stretched a little bit on all of these axes. And it's not colored like brushed metal yet. Right now, I'm only concerned with the shape and not the color. And the shape, I want it to look like the brush strokes that go most of the way across and are very thin, but don't go all the way across. And so I'm using that squished and stretched fractal cloud texture to get that shape in there. So that's great. What does any of this have to do with glTF? glTF can't do really any of this, right? It can't do fractal textures. It doesn't do complex node combinations like this. So what we're going to do is we're going to bake this to a roughness map. But let's start by getting it applied to the model first. We're still on our test cube. I'm going to take these guys and hit Control-J to join them together. And I'm going to call this brushed metal. So there's our brushed metal frame right there. And we will copy that. And I'm going to turn off our noise test object, and we will go back to looking at our CubeSat. There it is, along with flap 1 of the CubeSat over there. And I'm going to paste this with Control-V. So now we have our brushed metal here, and we'll plug it into the roughness channel. I might not get the result I would like plugging it into the roughness channel, but let's take a look. Well, it's very streaky, and I see some shadowy shapes. Let's see. If I unplug this for a second, I'll show you. We do have a reflection map. This is just Blender's default. We're in a forest with trees reflection map here. It's not really
Doesn't apply to CubeSats?
Doesn't apply to CubeSats very well, but it does let us at least see what the roughness values are. So I'm going to stick with it for right now. So one of the things I don't like about it is that we are getting these patches of extreme 0 and extreme 1, and that's too much for the roughness channel. To me, the sweet spot for roughness is somewhere between a little bit above 0 to maybe about half. So I'm gonna start by bringing this. So this node I've zoomed in here is the map range node. Remember we mapped our input values of -1 to +1, but rather than mapping them all the way to roughness 0, roughness 1, I'm going to bring this down. Ooh, not that much. And now we get sort of a streaky metal, maybe more like that. And then I'm going to bring up the minimum roughness. What do you think? So I'm letting the roughness vary only between 0.2 and 0.4. Those values are very close together, and these are small variations in the roughness.
Yeah, I'd crank that max up just a little. Perfect. Yeah.
Yeah.
That looks good.
So, and let's look at the pocket, as we decided to call it, only because we have no idea what that really is. So it's looking sort of like some sort of brushed metal here.
Now, how did this get applied to the side rails?
That's a good question. It's stretched differently on the different axes. So on this one rail, it's stretched a little this way, but it did get applied, and I don't have a light source down below, but it did get applied to the bottom as well. I don't have a good way to show that right this very second.
Could you show? I guess one way to show is we could bake this into the roughness map and take a look at the map.
I think that's where we're going to go next, because this, as it stands, is a cool fractal texture that cannot go into glTF. So we're going to bake it to an image instead. So let's start by creating a blank new image here. And this will be CubeSat rough. This will be our roughness image. Your textures should be a power of 2 for real-time rendering. They tend to like that better. I'm going to pick a UV grid. It's not going to matter, though, because we're going to overwrite that. So that's our blank new image called CubeSat roughness, or CubeSat rough. And we need to tell Blender that we intend to bake that image. So to do that, I'm going to make a node, an image node. And generally the flow of nodes is left to right, and I have a habit of placing my bake targets to the right of everything else, just to sort of visually indicate that they are an output node. I will pick my CubeSat roughness, and very important, roughness is not in the sRGB color space. I'm going to mark it as non-color. And that setting is not on this one node. That is actually an image setting that gets applied to this roughness image within Blender. So I have that. Now the other thing I've noticed about this is that I really want to bake Flap 1 as well as CubeSat, but I've not had much success, and maybe this will get fixed or changed in a future version, but I've not had much success baking to multiple objects at the same time. So I'm going to duplicate my CubeSat and call the duplicate my bake target. I named it bake target 1. And then I will also take the flap. I will duplicate the flap. And the copy of the flap, I'm going to flatten it out. For baking reasons, since we did a lot of axis-aligned stretching, I'm going to flatten this out to 90 degrees, like this. And I may even move it out, because when you're baking, a moving part doesn't need to touch the other part. If it did, of course, the noise coordinates would be very similar between the hinge and the top of the CubeSat, because these coordinates are all coming from world space. So I actually want the hinge to be in a different world space from where it connects, so it doesn't look like it's blended in as part of the same piece of machinery there. It's a different piece of metal that just happens to be nearby. So I moved it away for the purpose of baking. So this is my copy of Flap 1. I'm going to select it and then multi-select with Control key and then Control J to join. So now my copy of Flap 1 has been folded into my bake target. And
so the purpose of this is so that we have one object with all of our geometry in there that we are going to perform that baking operation against.
Yes, we have one bake target object that's standalone that has all of the geometry that I intend to bake, altogether. And let's go look at the materials on that object. The materials, I have a circuit board. Let's go to our shading panel and look at these materials. I have a frame material, which has my my bake target. I'm going to copy that. I want that same bake target node to exist in all the materials that I'm about to bake, even though this one, we didn't do anything with the roughness yet. Maybe we should do something with the roughness of that. Since we're going to bake it anyway, let's take the time to, our circuit board is this blank yellow, and it doesn't have any texture to its name yet. We may as well.
Yeah, let's put some roughness on there.
Yes. So I'm going to, from my brushed metal, I'm going to multi-select these guys, copy them, and we'll come over to our circuit board material, and I'm going to paste them in, plug them into roughness as well, and we get these sort of streaks along the side, but I don't want them to look the same, so I'm going to set these back to 1 so we get sort of that cloudy texture back again. It might be a little low contrast. I'm not sure how well this comes through. And the circuit board is certainly rougher than this metal, so I'm going to crank up these values here.
And you're okay with the Lacanarity of 2?
Yes. Lacanarity of 2, I think you always keep that value. I don't actually know of a good reason other than my demoing of the picture-in-picture effect. I don't know of a good reason to use anything much different from 2.0 Lacanarity. I know you just wanted to use your vocabulary. That was very good. So this is my cloudy roughness. I've used some different minimum and maximum values here. So I start at 0.5, which is already very high roughness. And I've gone all the way up to 0.8, which I consider to be extremely high roughness. And that's my circuit board. Okay. So I think we're ready for this. I'm going to select. Now you notice when I select nodes, they get this white outline. When we use the baking tool, the image that we bake to actually has to be selected with that white outline. And we're going to bake both of these materials. So I make sure that that node is selected in both. And then we're going to come over to the rendering panel, and there's not going to be an option to bake. We're still set to the EV rendering engine, which is a real-time rendering engine. And indeed, we're targeting real-time systems and real-time glTF and all of that. And I'm going to switch to Cycles, which is an amazing path tracing engine that has nothing to do with interactive real-time rendering for the most part. Cycles is a really cool path tracer, and it's a good thing to bake with because it will do all of the computations with a lot more precision. Eevee has been really nice to us and showing us this roughness done in real time, but Eevee is a very sophisticated real-time rendering engine, and not everything that does glTF knows how to do what Eevee can do. So we're going to use Cycles, which is going to bake all of this into an image for us. So let's choose roughness as our baking target here. And there's an option called selected to active. I'm not doing that. I just have the bake target 1 as my active object, and these the roughness image as my active node. So I'm going to hit bake on that. And Cycles will go ahead and bake us an image. And here it is. And you can see that the circuit board part of our image got to be very light colored because it has high roughness. And here are the top and bottom of the CubeSat. They got to be darker, so they're much smoother, but they have long streaks on them. So we hope they look like brushed metal. Now this image is just a temporary image in Blender. I'm going to go up to the image menu and hit pack, and that packs the image into the Blender project itself. I could also go and hit save as, but right now I'm fine with it just being a packed image in my Blender project. So let's go hook this up now. Before I do that, in my bake target, I want to save these materials that I used with all of my settings to do all of this baking. And to do that, I'm going to select these materials, and there's a button here showing the number of users. I'm going to hit that to make this a single user material. This is going to be a single user material, and I'm just going to add the word bake onto it. So this is frame material bake, and I'll make this one single user also. And I'll make that one circuit board bake. So now we have these two materials here are separate from the rest of our model. And in case we decide to come back and tweak some of these parameters and rebake them, if we want to change some of this later, these materials are going to stick around as is for us to come back to later if we ever need them. But for now, I'm going to turn our bake target off, and we will turn on our CubeSat. And this is our CubeSat. And it has, let's select it, it has our original materials, which I'm now going to actually remove our beautiful textures from, sadly. There they go. And gone. And now we're back to our placeholder materials. And what I'm going to do is I'm going to take this image that was the one that we baked, and we're going to plug this in as the roughness. Like that. That was the circuit board one. And we got our circuit board roughness is now coming from an image and not coming from the fractal nodes. I'm going to hit Control-C on that and go over to frame. And we're going to plug this into roughness there as well. You'll notice now that these the two materials I've got on here are becoming more similar. The circuit board has roughness coming from an image, and the frame material has roughness coming from the same image. These are getting closer to being the same material. The main differences now is the metallic value is different between the two of them, and the base color is different. And if we were to then bake those images as well, then we could end up with a single unified material where we would actually get rid of one of these material slots and just use a single material slot that would be a combined circuit board and aluminum frame material. And that would save our rendering engine a little bit of processing power there. But let's see how well this worked. So we have our materials with our roughness map embedded. And I'm going to try exporting to glTF. But before I do that, let's go back to our layout view and make sure that we have the right stuff selected. So I'm going to hit Shift-click on this eyeball to turn all of our pieces on. The CubeSat is turned on. The bake target is off. Our little noise tester cube is turned off. I'm going to hit A to select all of the things that we are trying to export. And we are going to export them to glTF. And earlier I had made a folder to store this in, and we're now on video 6 here. The settings are the same as before. I'm going to only export the selected objects because I don't want the bake target and the noise test cube coming out. And I also have apply modifiers in there because I had done some goofy things with normal vectors earlier. So let's hit export and see how that goes. And it will export my images. This version of Blender is a little bit slower. There's a future version of Blender coming that's going to have a pretty good increase in performance of texture exporting speed.
I should mention that Ed actually contributes to the glTF exporter plugin, so no one would have noticed that was slow. only you.
I would have. No, other people noticed.
Wow. Okay.
But thank you.
Yes.
So let's see what happened. This is the one we did today. I'm loading it up just into the Windows 10 built-in glTF viewer. And I just wanted to see if it would show us.
Well, it's actually a 3D.
The 3D viewer.
Yes,
it is a 3D viewer built into Windows 10. And it can handle glTF and a couple other formats. And it is indeed showing us. You can be certain this viewer doesn't know anything about a Musgrave 3D procedural fractal noise texture. But it does know how to read the image we baked with cycles. And it's showing it to us in real time. And let's see that it's put that same image on these little pockets as well. So it seems like it did a good job exporting that to glTF.
It looks great.
It looks great. Should we load it into SDK just to double check if it works?
Yeah.
Let's try it. I'm going to create a satellite.
So this is Systems Toolkit.
Yes, you describe it while I build a satellite. Describe all of SDK. Go. On the spot.
So what is a satellite? We're going to cut all that.
Yeah, we're going to cut this part. So I just created a satellite, and I've found the CubeSat here, and I'm going to hit apply. I also need to flip it over.
Actually, can you zoom in just a little bit?
Sure.
So the sun's not going to be down on the surface of the Earth, so maybe it is facing the right way.
Maybe it is facing the right way. Yeah, I think it is. So satellites and space vehicles fly typically in this configuration. So for example, if you've actually seen the space shuttle, if you've seen a visualization of how the space shuttle actually flies when it's in orbit, it flies with the cargo doors pointed down at the Earth. It flies upside down, if you will. And likewise, most satellites, when they sit on the ground, they sit on the ground in the assembly bay with their antennas pointed up at the sky. And then once they launch, the same antennas point down at the ground. And so if you put something in orbit in SDK, you'll see it flip upside down. And I'm going to actually make it a little bigger than real life because I would like to get some finer control over positioning. But let's take a look. Oh, now we can actually take a look at our brushed metal on the underside of the thing, and we see it having its metallic shine there. We see some earth reflections happening on these side walls here. And then if we can find one of these little pocket things, they're all sort of in shadow underneath. But I might be able to...
Yeah, reflecting the atmosphere back up.
That's the sun over there. So maybe, yeah, these things are all just reflecting the Earth's sort of blue atmosphere, and it's not quite doing what you might expect. It's just reflecting a bunch of blue light from down on the Earth. We're not catching a sun glint on that because it's facing the wrong way. But that's our satellite in SDK. So there we have a procedural texture that started off as fractal noise that could only be visualized correctly in EV and cycles and not in glTF. And then we baked it, and now we've exported it to glTF, and you can see it in all sorts of other applications that accept and render glTF files. Stay tuned, and in an upcoming video, we're going to take a deeper look at SDK and how to make these panels articulate and move, and how to customize this model a bit for use with SDK.